Okay. Okay, go ahead, Werner.
Yep, there.
All right, perfect. So first of all, thank you to Tim and Etikan for to join us here for the presentation, and also thank you to Andrew, who really pulled all this together, and who is also on the call, Andrew from XENON Systems, and we'll be happy to answer any questions at the end as well. So the topic of our presentation today is privacy preserving AI medical imaging with federated learning. And yeah, let me just jump straight to the next slide, give you a very brief overview of who XENON Systems is, and then we'll go into the core presentation by Etikan and Tim. So XENON Systems being a systems integrator, consultant, and infrastructure reseller. We've been around for 25 years and have been working with a variety of customers around the country. That includes CSIRO, NCI, Thales, pretty much all the big universities around the country. And probably more important here for this forum and for the audience here at the conference are, of course, our customers and partners in the deep learning and AI space. And if you just want to jump to the next slide, where we give a brief overview of kind of 4 even more relevant customers and projects which we can reference here. So we've been working very closely with the Walter Eliza Hall Institute, for example, where we have deployed a virtualized HPC infrastructure that's been serving that team extremely well. That also included NVIDIA GPUs, and they're running a lot of genomics and also deep learning and AI workloads on that system. More recently, one of our big customers is also Harrison AI, and they have really a wonderful implementation, which you've probably heard about in the news, where they are doing deep learning and AI to analyze especially X-ray images. And that's all running on NVIDIA DGX infrastructure, which we have worked very closely together with NVIDIA to put together, to deploy, and to run for this customer. In addition, the Garvan Institute, for example, has been at the forefront of medical research, of course, for many years, and they have deployed a variety of infrastructure from XENON Systems, which we've installed there. In addition, also the Murdoch Children's Research Institute, where we've deployed a large data management solution and also backup infrastructure. So with that, XENON Systems has been around for 25 years, working with a lot of customers in medical research at the universities and also hospitals. And we're really very proud of our partnership with NVIDIA. And last but not least, of course, also for our partnership with Tim Wang and his team. And with that, I'll hand it over to Etikan, and then Tim will follow up and give you insight into how he's been using this technology in his institute.
Thanks, Werner. So it's a great partnership between NVIDIA and XENON there in Australia, and they've been a very good partner for us to make available GPU to all the research community, plus also now in the deployment space. So my name is Etikan. I'm responsible for developer and researchers engagement in the region. I work with some of the leading institutes in the region together with the researchers to bring the technology into production or into applications. I call it as a translational research engagement. I'm going to share briefly some of the journey that NVIDIA has taken in the last 25 years in the space of AI. We are one of the leading entity in the space where we provide the compute platform as an AI platform company, and coupled with many of our SDKs and platform. I just want to share recently some of the work that NVIDIA and our partners have done together. For example, in the space of medical imaging, we have seen vision transformers. As you know, some of the models, transformers usually used for natural language processing. But recently, we have seen a good and great breakthrough where transformers can provide better accuracy and also performance for medical imaging. In the space here, an example of UNet model. And on the other advancement that we have seen, for example, FDA has approved first prostate cancer detection AI algorithm. I think this is something significant and very important for all the researchers and also developers globally, where you get the recognition and also acceptance in the space of applying AI in your day-to-day activities. So beside that, we have seen interesting work being done, for example, in Peking University using graph neural networks. So GNNs is something which is very new, adapted for a node-to-node type of communication understanding. But now we have seen GNN being applied in medical space. Finally, one of the areas that NVIDIA has been pioneering working globally, which is called Federated Learning, which is the focus of today's discussion. I'll go into that example later. These are the key highlights of what we have seen, the latest breakthrough in the recent months across the globe. Now, how does NVIDIA work with the research community like yourself, either from the hospitals or from the teaching hospitals or from universities and so forth? So we adopt an open source approach where we provide the medical AI framework to all the researchers so that you can use the framework and accelerate your R&D work. And this particular framework has been maintained and also optimized by NVIDIA, and we make it accessible to everybody. So the work is being done as a consortium, and this is one of the pioneer initiative we started together with the King's College initially. Now we have seen large number of developers are joining us and adopting the MONAI framework. If you can see in the graph, in the last less than 2 years, we have seen almost about 140,000 researchers, developers are using this MONAI framework. It comes with many features. So we call it as NVIDIA Clara component that actually goes as part of the core component of MONAI. Again, it is open source and can be used by everybody in the research community. It has automated AI, annotation algorithms. It has many optimization techniques and methods has been implemented. For example, Federated Learning technique has been implemented. We have a multimodal training as part of the package as well. We have AutoML component has been integrated. Ease application deployment also being done by part of the framework. And finally, you also can do media streaming from external device into the medical device or into experimental device where you're actually analyzing the video streams using AI. And this is fundamentally supported by our many open AI frameworks. You know, it could be PyTorch, could be TensorFlow, any of the open frameworks, and it runs on top of our accelerated SDKs and platform, like for example, Triton, TensorRT, and DeepStream. And it is easily accessible. You can actually deploy these SDKs and Clara SDK either in a cloud or in terms of on-prem, where XENON, actually our leading partner in Australia, making it available so that it can be done in a secure manner. And also it can be integrated together with many of our solution partners who can provide assistance in terms of developing your own custom tools, for example. This is just an example of some of the hospitals, leading hospitals in the world, which adapted MONAI, and also the DGX systems, which comes with the multiple GPUs, where XENON is making it available. This is just in a few examples. We have seen across the globe, many countries as actually have adopted and using AI as part of their continuous research work, including in Australia. This is just an example of how Federated Learning as one of the library components that we make available as part of the Clara framework. So what NVIDIA has done, we worked with about 20 different sites globally, 8 different countries across continent. We partnered with the respective hospitals and in those countries, and we actually developed a model for COVID-19 oxygen prediction. It took X-ray, chest X-ray is one of the input, and also other data sets could be like, for example, is a blood test results, oxygen saturation result, blood pressure, and so forth. So these are EHR data set combined together with the medical imaging. Then we did the Federated Learning on this particular data set to provide a prediction outcome that we are looking for, which then can be used for various resource planning or various type of prediction purposes. And if you can see, the global model that we have actually trained is converged with the 0.93 AUC, which is quite impressive, and it was really useful to all the participating partners. Where the global model now, it is made open. You can actually get it downloaded from NVIDIA websites called ngc.nvidia.com. So just an example how the model that we, the platform that we developed, we ourselves took it to the field. We tested with the partners like yourself and the rest of them globally to make the Federated Learning platform applicable. So how does it work? It's very simple. Each and every participating hospitals may have their own data, which is a private data. They can't share publicly, or they can't share even to the other collaborators. And they have the local compute capability, where the local compute capability, for example, in this case, it could be a DGX server with the multiple GPUs. You develop your own model, and this model then will share the local model into a federated server, where global model being designed and developed. In this case, the data does not leave the premise, only the weights which the local data actually collects over a period of time being shared and converged as a one global or supermodel. I call it a supermodel, where the supermodel then can be shared across local sites so that they can actually leverage the local data inferencing using the global model. There is a publication on this particular work. It's open, and you can take a look at it as shared over here down here. And also a recent publication we have done in Nature's journal. So before I pass the session to Tim, just some of the technical consideration that I would like to suggest for the participants to look at as you use Federated Learning, and also various features and functionality which comes in. From FL perspective, in terms of privacy and security, so FL actually provides secure manners where you can train your local model and then exchange only the weights with the global model. But in some cases, some of the organizations don't even allow some of the weights to be shared externally. So if such regulation or policy in place, you may want to look at those privacy policies where even only a fragment of weights not being shared, or some of the fragments of the weights can be shared for a specific data set. In that case, as part of the Federated Learning framework, we allow yourself, as a user, to decide which part of the data set could be used as part of the training mechanism of the model. So that what does it mean? We give you the key to decide which part of the data set can be used to do the model training. So these are fine tuning of the privacy and security component that you can actually turn on, turn off based on your needs. So FL does not solve all privacy issues because privacy is subjective to region, country to country, even to the hospital respectively, right? So I would like you to look at those and then adopt FL as what is possible and what is allowed in your specific environment. Now, next, depending on the level of trust in FL consortium, because you're working with multiple partners and also sites, you may have, the consortium may have your own confidence level and what actually allowed to be shared among your consortium members. That's something to be considered as well. And additionally, we actually made possible or made enable homomorphic encryption. So that means you are not actually training the neural network model on the actual data set, but actually the model is being trained on encrypted data set. As you know, homomorphic encryptionism is a means of encrypting the entire data, where the data is not being exposed, even for the local data training. It's the mapped information, which is the coherence and consistency being maintained, used in order to do the model training. This is an additional option made available so that you can use it for your model training. Data heterogeneity is something you may want to consider, because when you work with consortium or partners, not everybody provides equal number of data sets or equal quality of data sets. Do consider that as well. And then traceability and accountability. We have, we just want to share with you what is the level of traceability that you want to have in terms of where the weights are coming from which sites, and how does the weight actually influence impacts the overall AUC. creation for your specific model that you're working on, because you may want to have certain level of integrity being maintained. So all this is our suggestion for you to look at as you start build the model across different sites. And also we have seen some cases, some of the sites may have some kind of a revenue model as part of the contribution to the overall global model training. So you may have your own means and mechanism how you want to measure their contribution, which then translate to revenue model. And in terms of system architecture, each of the local training site need to have compute capability, sufficient compute capability based on the size of data they are contributing, and also frequency of the model being constantly updated to be shared. So with that, I'll pass it to Tim to take it from here.
Thank you very much, Edkan, and thank you, Winner. So maybe Edkan goes to the next slide.
Yep. Okay.
Yep. Yes. So basically, the next part would be me to bring you the some of our experience, our local experience in Sydney, how we, using those techniques and especially federated learning in the real world practice. And I will demonstrate with you with a couple of cases. So my name is Tim Wan. I'm one of the co-founder and also the director of operations at SNAC. And we actually coming from the background of providing the commercial imaging services, analysis services for pharmaceutical company for their phase 2 to phase 4 clinical trials. So that means we have accumulated a very large experience on how we deliver either AI solutions or conventional solutions to the clinical radiology. So maybe some of our experience in terms of data privacy preserving and also security, you maybe found them useful. So maybe next slides, Edkan. Yes, so if we're looking at the entire journey of how we approach AI in medical imaging to deliver them into a hospital system as commercialized and also TGA FDA approved tool, we usually start, of course, to identify the clinical needs, whether the AI model you're looking for is to improve productivity or accuracy or other type of purpose. Then you bring that needs of the clinic needs into the AI tasks. You get your AI scientist to do the detection, classification, segmentation, or any other type of AI tasks. You may have found a lot of the time, a lot of AI work really stops here. You may found, just for example, in this year's MICAI, there is probably 99.9% of the paper or deep learning tasks, deep learning in medical imaging, but you can see the landing of many of those really amazing solutions that still stopped at this level at the publication is because the next stage, which is the delivery, is equally harder a lot of the time than the data itself, than the model itself, because we're concerning the seamless clinical integration. That means the needs really how we make those AI algorithms to be user-friendly to the doctors. You're not slowing them down, you actually improve their productivity. And also, of course, the data security and privacy. So that's this seamless clinical integration and the data security and privacy the cases that what I'm going to talk about is focused on this stage of the entire AI journey. And many of you probably already know the regulatory, of course, also the business model is interesting. Maybe that is leave for the next stage. Yes, so for that specific purpose, we formed a task force last year, how to deliver the AI solutions into clinical practice. So essentially, this is we call a Transcend initiative or program with really amazing team we put together around the University of Sydney, IMED, SNAC, NVIDIA, and XENON, and a couple of others, really focus on the clinical outcome, and particularly in neurological disease. So I know some of you probably working in the cardiovascular or in the neurosurgery, and please don't leave. This is still highly relevant to you because some of the solutions they may find them useful. And also, of course, that is our first target. And second target will be the central federated ecosystem for sustainable AI innovation. So that means the system we put into the hospital system is not only that we want them to be used as we want it, but we also want to collecting the user needs and continuously evolving the AI innovation in the hospital system. I will show you a little bit more. You probably see, will see what I'm saying. Yes, so those are three elements is today I wanted to show you what is our experience in terms of what we have done before and how to perform large scale multi-center, multinational AI training and before, and of course with considering the data privacy and security, and then how we gradually it's actually met the needs of a federated learning, why we need a federated learning, and how we incorporate federated learning within the existing system. And then the next stage last is not only we build the models through the central or federated training, but also to use in the clinical. And next. So the first, of course, I would like to show you this example is the MS-based imaging repository. So this is actually a large research imaging platform we built with University of Sydney and MS-based, which they hosting basically over 75,000 MS patients across the global with almost 38 countries. So they don't have the imaging because the imaging is starting getting very important. So that is the from last year was starting building this imaging platform together. So, and on top of this imaging platform, we gradually also pushing forward to the solution of AI, artificial intelligence framework. And you can please next slide. So essentially, the centralized training is very simple way of AI innovation. Of course, you're collecting the data from all of the clinics, but within this workflow, these are the common needs that actually we put into the place to collecting the data to the central server. So of course, that involves the data anonymization, security, and also you wanted to make sure and all your imaging is after anonymization still matching with the clinical database, and you always have a link to the clinical database they're using in the hospital, so you can always accurately retrieve the imaging information to match with the clinical information. And of course, you also need, the most important is to link with the hospital infrastructure, and regardless actually what's their system, what packs and the scanners they use, you need a generic and one for all type of solutions to link their equipment. And of course, there are some QA step in place. I can show you a little bit later. Yep, and maybe next, Edican. So this diagram is the one thing I would like to really to show everyone. This is the basically summarize the key elements of how we handle the data privacy and security in terms of the central imaging repository configuration for AI innovation. So essentially, if you look at the right side, the MS-based imaging repository, this is the centralized data server hosting all the data. And on the left side is the hospital intranet. So the most important trick we're doing here is this called Turana piece of software or framework in place. So what happened is regardless of what the imaging information in the hospital will retrieve to send to the center, we always anonymize them locally. So I know some of the people participating in the clinical trial, you anonymize the data yourself, but here, what we built here essentially is the fully automatic system that basically strip out all the key sensitive information, sometimes also include the defacing for the brain imaging to remove the face from potential identification of the patient, and sending the data to the central imaging repository for either archive or analysis. So all the researchers later can deal with this imaging central repository altogether. And the next slide, I will show you what's inside of this Turana software. That's so a couple of the important things in this centralized imaging configuration. So first of all, you have to, concerning of course, the secure scan routing, right? The anonymization and the re-identification. So basically what it means is once your imaging already sent anonymized, but when the analysis result is returned from your AI model, wherever it's sitting, it's needed to be re-identified, sending back into the system. Of course, there is some quality checking, but I can probably, concerning the time, I'll probably just move on. Yep. So once we have this centralized imaging repository, we gradually start realize actually some of the training is still not enough, because some of the jurisdictions, that's even not the data, the raw data to leave the country from memory, like Germany. So that means we gradually developed our data archiving system federated way as well. So essentially different jurisdictions hosting their central servers and the data were hosting them. So that means, and when we start training our central model together, we really need something to matching with the federated archiving system. So then that we start looking at the solution of a federated learning. So basically allow you not to share the data, and you're still able to train the data locally at the different centers, different hospitals, and the different XNAT, which it means the imaging archiving system we're using, and then merge the model together. So next slide, I will show you what we put into the box that in the hospital. So they are using. So they are using help them to facilitate all the data logistics, their research data archiving, annotation, and federated learning. So basically, you can see those on the left side. Essentially, Torana handles all the data logistics, integration with the PACS system and RIS systems. XNAT is the research archiving, data archiving system, basically systematically hosting all the research elements of each hospital. So you just need one and managing a vast number of different projects. And of course, ITK and of course, other type of software allow you to do the annotation. I think and NVIDIA also have an amazing AI-assisted annotation tool as well. So allow the analyst or radiologist to annotate your data and for training purposes. And of course, lastly is the federated learning component from the Clara that allow us to integrate all the data and to achieve a federated learning. Yes, please, next, Etienne. Next slide. So this is to give you the flavor of the total data flow, how the DICOM data move to the federated learning. So essentially the hospital, once they acquiring the data, the first time they will sending to is the Torana server within the hospital. And the Torana will perform all the security checks and also data QC, and also understand the task of what data is for, sometimes sending to neurology, sometimes sending to the radiology department, and then archive them, categorize them, archiving the central research component, which is the XNAT. And XNAT will, based on the tasks required, working out the work list type of priority between different AI tasks, some sending to the for segmentation, sometimes sending for central training, and based on the different tasks, or sending to the processing server. And the processing server will eventually end up sending all the data stream into the NVIDIA Clara system to perform federated learning or even local training tasks. So this is the, concerning the time, this is basically the overview of how the imaging the training tasks have been achieved. So these slides, I just wanted to quickly show you once the data training has been done, the AI model has been established, how we implement the AI model into the hospital system. I think the key message here on this map essentially is the reassociation components analysis here. If you look at the left in the hospital intranet. So yes, the key idea essentially is once your data stripped out all the sensitive information and encrypted at the Torana, sending out for any type of analysis engine sitting at outside a hospital PACS system or outside in the central another analysis place. The important thing is the encryption or the matching elements allow the analysis result when it's returned, it will be reassociated with the stripped data. And that stripped data will matching with the patient's information database, allow the doctors to review the AI results. They don't need to install any software. They just can look at those results in their original PAC and RIS systems because the key information carries those analysis results, still the DICOM format, still the data that most of the PACS and PACS system use. So essentially, this is the probably concerning the time, this is just a very quick example demonstrate how the subtraction imaging analysis is being used. If you follow the workflow, how the data received, stripped out the sensitive information, sending to the analysis engine, and returning to the Torana to be re-identified and feed back into the PACS. So essentially, this is the one of the small sort of algorithm we developed to comparing the baseline and the follow-up brain imaging differences, help the doctors to quickly identify the new pathology, the growing of the lesion, the growing of the tumor, etc. Allow them to quick pick up the differences between the imaging. So this has been achieved under this framework. Thank you very much. That's all my part.
Yep. I think I'll end it here. And pass it back to the presenter. Just the last one video clip, if it is allowed, just to share this is what NVIDIA is working on now in terms of integrating the AI robotics together in the medical space. So if you can see, we are working with some of the partners together where they have the streams coming in from the video devices. Could be integrated together with the framework that we provide for specific type of activities. So in this case, this is a HoloScan, is one of their components that we actually put together for visualization rendering, and then integrated together with other component, for example, in the voice activation. Right? So the person over here could able to talk to the Clara component system to remove the reps automatically. Right. So there is a lot of works being done in this particular space so that integrating AI devices into a single system. So this is some work is being done continuously with us and partners, and we are actually making this Clara HoloScan and SDK open to everybody to adopt. With that, thank you.
Right. Thank you so much, team Werner and Etika, for